Okay, in this video I want to talk about the composition of linear operators. I hope you remember what the idea of composition of functions is, because that's exactly what we're dealing with in this case. Let's go ahead and say L1 is mapping r to the m into r to the n, and L2 is mapping r to the n into r to the p. Okay, so these are linear operators. Okay. Use T's if you like transformation, that word better, but whatever. Okay? Now the composition operator, L2 composed with L1 is defined in the following way. Okay? First of all, we know that L2 composed with L1 is going to, map r to the m, the original domain, into what? The final codomain here. Okay, so the range itself ultimately is a subset, maybe a proper subset, maybe not, but a subset of the codomain. That's r to the p. Okay, so you see the mapping's going to go like this. Okay, to help see that here, just to remind you about composition, if I say L2 composed with L1 of x, where what? X is coming from r to the m, right? It's coming from there. Okay, what do? Well, all you do is you take L1 of x first, right? And you compute what that is. And then that result goes into what? L2. Okay? Now, when I take L1 of x, okay, what pops out? A vector in Rn, right? Okay? And then that vector from Rn drops into L2. And then what pops out? A vector from r to the p, or rp. Okay? All right. So that's why we have it ultimately going from what? R to the m, or rm, to r to the p, or rp, if you like that better. Okay? All right. So this is what we mean. That's all we mean by the composition. Okay? This. Now I claim this is also a linear operator. Okay, the composition of linear operators is a linear operator, or linear transformation, if you like that word better. Okay, let's just do it here. Let's prove it. Okay, L2 composed with L1 of a times x, right? A is an arbitrary scalar. X is coming from r to the m. Okay, well, what would happen? This is actually what it means. It's L2 of L1 of a to the x, L1 of a to the x. I can pop that what? Scalar a outside. That's not dot product, by the way. That's just multiplying. That's a times what? L1 of x, right? Okay, I'm going to take that out just so you make sure you see that's not a dot product. That's just a scalar multiple. Okay, anyways, that's a times L1 of x. Okay, but wait, L2 is also linear. So that means that scalar a can pop outside that. Okay, so that's a times L2 of L1 of x. So that's a times the composition of L2 and L1 acting on x. Okay, all right. What else do we need to show? We need to show that the composition is additive. So let's go like this. L2 composed with L1 of the sum of these vectors x1 or x plus y from r to the m. Okay, so this is just what it means. So L1 is acting on x plus y, but we know that that's additive, right? All right, so that's going to be the L1 of x plus the L1 of y. Okay, so that's the sum of two vectors also. Happens to be in r to the n. L2 is going to act on those because it's additive also, right? Because it's a linear operator. L2 would act on L1 of x first, and then L2 would act on L1 of y. Okay? But that would mean what? Oh, wait, this is just the composition. L2 composed of L1 of x, L2 plus L1 acting on y there. Ooh, that means it's what? Yeah, it's additive, right? Okay? This means it's what? This is a linear operator, so this is also a linear operator. So we've proven this statement here. Okay? What does that mean? Well, if it's a linear operator, we know it can be represented as what? As a matrix, right? Essentially, as a matrix product here. All right, and I just say that here. Every linear operator between finite dimensional vector spaces, I'm talking about here R to the, K, where K is a finite number. There are infinite dimensional vector spaces, by the way. Okay, but I'm just talking about these guys. Okay, can be represented as a matrix product, so we proved that in a couple videos ago. What is the relationship between the matrices for L1, L2, and the composition? Okay, well, it's going to be easy, actually. Okay, again, we're back with we're still doing this. Okay, we're still doing this. All right. For x in R to the n, right, L1 of x is some vector, or some matrix A1 times x, okay? This would be what a matrix, it's a real matrix n by m, right? Okay, because it's taking what? M vectors and turning them into n vectors, okay? So A1 would have these dimensions, okay? Now, for y is an element of R to the n, L2 acting on y would be what? Some matrix A2 multiplied by y. Okay, A2 would have to be what? Have the following dimensions, a real matrix P by n, because it takes what? N vectors and turns them into P vectors. Okay, just pointing this out. Now the composition of these two, okay, we know that means that. So this would just be what? Instead of saying L of x, L1 of x, I'll go A1 times x times, right? And then that drops into L2. But instead of L2, I'll say it's A2 times A1 times x, okay? Now you guys already know that what? Matrix multiplication, these are just matrices. Matrix multiplication is in fact associative, so I can actually move my parentheses over here and multiply those two matrices first, and then what? Then multiply by the vector x, okay? Well, you think about it here, look at the first and the last. Look at that, and look at that at the end. This is saying the matrix representing L2 composed with L1 is A2 times A1. Okay? By the way, you just look at the dimensions here of A2 and A1. Okay? If I go A2 times A1 from the dimensions here, you can see that the dimensions of A2 times A1 would be what? P by M. Okay? P by M, just like we expect, since L2 composed with L1 maps Rm into R to the P. Okay? So that is just a short video here showing you the relationship between these matrix products and linear operators in composition. Okay? Well, I hope you understood that.